I'll share my screen. So that's the notes, second part of the notes from last week on acoustics. Can you see them?
Yeah.
Okay. Any questions so far from last week?
Not from me.
Okay. All right, well, let's just get cracking. So internal ductwork insulation, we have talked about this before, but I'll just go over it again. Acoustic attenuation, the insulation this is for internal ductwork insulation as opposed to external insulation. So the internal insulation has various uses. Firstly, acoustic attenuation. It's normally faced with perforated foil, which allows the sound energy to be absorbed by the insulating material and prevents insulation fibres from entering the airstream. So the perforations allow the sound energy to pass through the foil into the insulation. Just be aware that on some projects you can't use perforated foil insulation for internal insulation, such as some medical parts of a hospital, for instance. If it's serving clinical areas, you'll probably find that the local hospital codes won't allow to use perforated insulation. It has to be an integral foil over the insulation, which you can do. You can get, I think it's called acoustic tough, which is not perforated. It does have some acoustic benefits, but you can use it in a hospital environment or in a clean room environment if you're using internal insulation. So there's some options there. Internal insulation is often used on small projects, so the ductwork can be totally pre-insulated in the factory. This means there's no need for a ductwork insulation contractor to attend the site. I'll just show you a couple of pictures of, if you haven't seen it. Have you guys been to a duct factory? I think you have, haven't you?
Yeah.
So you probably saw them doing this, did you? Doing the internal insulation? Okay.
Yep.
So that's in the process there. There's another picture here of what it looks like basically when it's finished. So they put angles or trims, flashings on the long sides and at the joints just to cover up the raw edges. So that's, sorry, just on that one, that's worth remembering. Some contractors may prefer on a small project just to use all internal insulation because it's easier on site. All the ductwork is delivered to site, pre-insulated. All they have to do is install it on site. They don't have to get another contractor to come in and apply the insulation. If air conditioning ductwork is exposed to view and requires insulation, internal insulation is hidden from view and protected inside the duct. Sometimes you'll have this in a, say, bulky goods store where you need to, for instance, or a shopping centre where the ductwork has to be insulated, but it's exposed to view. So you're better off to internally insulate it because then you can't see it, it's protected, and it gives a better finish. Also in plant rooms, ductwork is normally internally insulated for protection and for acoustic benefits. I've just noticed there's a guy outside with a brush cutter, so there might be a bit of noise coming up shortly, but I'll try and work through that. Now, acoustic attenuators are basically internally lined ducts. The insulation thickness and density is usually greater than the standard ductwork, and the insulation material is contained under perforated metal in this case, not perforated foil. They use perforated metal to ensure the insulation, to ensure the attenuator is robust, or the insulation is robust under relatively high air velocities through the attenuator. We'll talk about this a bit more in a minute, but velocities through the attenuator can be quite high, up to around 15 meters a second. If you use perforated foil, it will tend to erode over time. It doesn't have much strength. Under normal low velocities, up to 8 or 10 meters a second, it's going to be okay. But when you're getting up to the high velocities, it will tend to deteriorate over time, and you don't want that to happen inside an attenuator because it's not really accessible to repair it if you have to. In some applications, an impermeable membrane, a couple of ones that are used are Mylar or Melanex, which is like a polythene sheet, is applied to internal insulation or attenuators. So the insulation surface is cleanable or hygienic or weatherproof. Some examples are in kitchen exhaust ductwork. So if you have an attenuator in a kitchen exhaust duct, you would always put this Mylar or Melanex inside. Sound attenuators exposed to the weather. If you've got one outside on a smoke exhaust or something, you'd probably have Melanex. And medical and clean room supply air duct sometimes has that too. When they're supplied, though, the acoustic performance of the internal insulation is reduced. So just be aware of that. If you're putting Melanex inside an attenuator, the attenuation will reduce. Oh, hi, John.
Hey, sorry, I'm a bit late. Just had to have a quick meeting.
No, that's all right. We weren't sure whether you were going to make it or not, but good to see you.
Yeah.
So we might have started. Sorry, John, but we have sort of talked about this stuff before. Internal duct insulation is often used for acoustic attenuation in the following situations. At the inlet and or outlet of fans, fan coil units, air handling units. I'm sure you've come across this already. And quite often in ductwork bends or changes of direction, where the change of direction provides enhanced attenuation. So that's just a quick summary of internal insulation of ductwork. Any questions on that? Okay, let's have a chat about attenuators. And if you've got any questions, just interrupt me anytime if you want to. If it's impractical or not possible for the internal duct lining to attenuate the sound to acceptable levels, then it's probably necessary to install attenuators in the ductwork system. This will give you much greater attenuation. I know that we do encourage you to look at whether you really need attenuators because they're expensive. But sometimes we have to use them because we can't get the attenuation we need by lining ductwork. So attenuators can be rectangular with splitters or cylindrical, with or without pods, and may have Melanex or Mylar lining if needed for weatherproofing or special applications, which I talked about before. So I'll just show you some extracts from the Fantech catalogue, in case you haven't seen what an attenuator looks like yet. So there's the two types, rectangular duct attenuators. There's two types here. There's an RS series, which has got straight splitters, or there's the RT series, which has got tapered, RT series has got the tapered splitters. And then there's RTQS. That means it's a tapered splitter. QS means Q-Seal. That's a Fantech brand. Q-Seal is with the Melanex lining. Basically, that's all that means. So if you go through this, this is in their catalogue. You can go through and find out all the data. just to give you an idea of what the terminology of an attenuator is, RT, tapered splitter, RS, straight splitter. Now you have different numbers, which is the airway width code, which is, if you look at these diagrams, that's the width of the airway between the splitters. So that's those codes there, 07 up to 25. Then there's a length code, A, B, C, C2, etc., which is the length of the attenuator, which is shown on that diagram. And then there you can have Q seal, which is the Melanix lining. So you can see from these diagrams the RS model has got the splitters are straight all the way through. They've got a bit of a bull nose at the entrance, so the air's coming this way, a bull nose at the entrance and then straight. The RT has got a tapered splitter at the exit, and that reduces the pressure loss as the air leaves the attenuator. The RT type is the one that we would use more commonly. The RS has a superior attenuation or insertion loss performance, but the pressure drop is higher. They're more expensive. The RT is the most commonly used one in the rectangular type. And then it goes through and gives you insertion loss data for the different models. So the different splitter widths, airway widths and lengths. And then that's the RS, and there's charts there for pressure losses, depending on the face velocity. I'll talk about that a bit more in a second. And then this is the RT. There's a much bigger range in the RT, but the insertion losses are lower by comparison. And then there's the RTQS, which is this one, which has got the Melanix lining. So it's basically an RT attenuator, but it's got the Melanix lining underneath the perforated foil to give it, to protect the insulation from whether it be water, chemicals, whatever the case may be, and to absolutely prevent any fibres from being released from the attenuator. So that's good information that's available in the catalogue if you need to select an attenuator. It tells you how to go about it. Now, the other one is the circular attenuators. So you can have just a cylinder, an open cylinder, or you can have the cylinder with a pod in the middle. The open circular one comes in either nominal one diameter length or 2 diameters length. You don't get much attenuation from these attenuators because basically that's just a piece of duct, but it's basically internally lined duct. The insulation thickness is usually about 100 millimeters, so it's better than a piece of duct with internal insulation, but doesn't give you a great amount of attenuation. These are commonly used at the inlet and outlet axial fans, and because it's basically a duct, they can be bolted directly onto the fan without affecting the fan performance. When you go to a pod, these give improved attenuation, but you need to have a duct piece between the fan and the attenuator to, particularly on the inlet side to the fan, because the pod will cause turbulence in the airflow, which will affect the fan performance. So you need to have a spacer piece, say 1 metre long of ductwork between the attenuator and the fan if you use this type of attenuator. We don't use these very often. They're quite expensive, and they can cause issues with fan performance. I'll go back to the notes. Now, we need to take care in locating the attenuators in the ductwork to ensure that optimum acoustic performance is achieved and the air pressure drop is within NCC Section J requirements. Where we locate the attenuator doesn't necessarily affect the pressure drop through the attenuator. We can select an attenuator for 40 pascals maximum, and that's what we have to do to satisfy the NCC. But the pressure drop through the attenuator will be increased if they're located in a bad location, such as right after a bend or after a branch, or fittings in the ductwork will affect the performance of the attenuator and will affect the pressure drop. So it's important to locate the attenuators as close as possible to the noise source to minimise noise breakout from the ductwork, but beware of fittings. Now, when you're selecting attenuators, going back to that data I just showed you, it's essential to ensure that the low frequency attenuation levels, particularly 125 and 250 Hertz, are achieved. 63 Hertz is given as an insertion loss on the data, but the acoustic consultants have always said, don't worry about the 63. The 125 and 250 are the ones to look at. And they generally cause issues and the most annoyance because they don't naturally attenuate. Sorry, I'm getting off the track here. These low frequency sound levels generally cause most annoyance and do not attenuate naturally due to the long wavelength of the sound. So low frequency is long wavelengths, which means a sound wave passing down a duct. The high frequencies are bouncing around, and so they're coming in contact with the duct walls. And if the duct is internally insulated, the attenuation of those high frequency sounds is enhanced. But the low frequencies have a very long wavelength, so that the sound will keep traveling down the duct with minimal attenuation, if that makes sense. So this is why you'll find that most noise nuisance is low frequency noise, because it's the hardest to attenuate. So just be aware that you're achieving that when you're selecting an attenuator. Now, the phase velocity of a rectangular attenuator should be around 5 to 6 meters a second. Again, pressure drop needs to be less than 40 pascals to satisfy the NCC. So when I say phase velocity for a rectangular attenuator, I'm basically talking about the duct velocity where it attaches to the attenuator. Does that make sense? Because what happens inside a rectangular attenuator is, because you have splitters, the air is accelerated. The velocity increases through the attenuator. So a good rule of thumb is to keep that around 5 to 6 meters a second, and usually the pressure drop will fall within that 40 pascals. That's not to say it always happens, you just need to check each one, but when you're doing your initial design, that's a good guideline. So when the air passes through the attenuator, the splitters cause the velocity to increase significantly. The recommended maximum passage velocity is around 15 meters per second to prevent unwanted regenerated or breakout noise and to keep the pressure drop down. So as the velocity goes up, the passage velocity increases through the attenuator, the generated noise will increase as well. And then so the attenuator is working against itself in that case, because it's reducing the airborne noise, which is the air going down the ductwork, but it's generating noise through the casing of the attenuator. So be aware of that. I'll show you something I've already sent you. I sent this document out by email to you. It's just general information about acoustics. This is quite handy to give you an understanding of sound power level, sound pressure level. And then it goes on to talk about insertion losses for attenuators. And there's a table here airway velocity. There's some recommendations here on the airway velocity you shouldn't exceed under these NR ratings. So NR40, 15 metres per second. As you go down in NR rating, the velocity is going down as well. So that's the passage velocity through between the splitters in the attenuator. NR45, they're saying 18 metres a second. Well, so you can go a bit higher. When we talk more about attenuator selections, this will become a bit clearer. Maybe I'll just talk briefly about it now. So with those codes that are given here, the airway width code, 07, 75 millimetres, 10, 100 millimetres, and so on. So that's the airway width through the attenuator. As those airway widths increase, that's going to help to reduce the velocity through the passage velocity through the attenuator. So if you've got a constant, if you're working on 5 to 6 metres a second face velocity, then as those airway widths increase, the passage velocity through the attenuator will reduce, and the pressure drop will reduce as well. Does that make sense? Pretty basic when you understand that. There is quite a process involved in doing a manual selection of an attenuator, and generally we don't do that. We work out what attenuation we need. We can select from their catalogue an attenuator that we want, and we can work out the pressure drop. So we can do all that ourselves, but normally we just send the information to the suppliers, such as Fantech, and ask them to give us some options. Now, just another reminder, I did mention this before, but noise sources are additive. If two equal noise sources are close to each other, the sound level will increase by 3 dB. If you have several equal noise sources in proximity to each other, that can have a significant impact on the overall sound level. Can anyone think of a situation where you've experienced that, where you have a number of similar sound sources near to each other and the sound level becomes almost, unbearable? It makes it hard to talk. No?
I know, just like being in a crowded pub or a restaurant.
Exactly.
I was going to say the same thing.
Yeah, that's an example, the same sort of thing that I was thinking of. If you're in the pub and you're talking to your friend, just the two of you, there's no one else there, it's nice and quiet, isn't it? But then some more people come in, they start talking to each other, the noise level goes up. More people come in, the noise level gets higher and higher. The same thing happens in restaurants, particularly if they've got very hard surfaces, hard floor, hard walls, hard ceiling, no soft furnishings, no acoustic panels to try and absorb the noise. It gets to a point where you can hardly talk to people, even next to you. It's just, I really struggle myself in those situations to talk to people because my hearing's not the best and my voice is not that strong to talk over a crowd. So that is a good example of what's happening. So if you've got, we'll say a plant room is probably a good example where you have a whole lot of equipment, a number of pumps, might have chillers, fans, all these things add to building up the sound level in the plant room. Now, plant rooms are not usually a big concern, but if you've got a plant room adjacent to an occupied space, then it is a concern because the sound in the plant room is going to pass through the walls into that occupied space. So we're not going to go into attenuation of plant rooms at the moment, but just to be aware that if you have sound sources close to each other, they do add, and that creates a problem. So a simple process when selecting an attenuator is, firstly, we need to determine the required or acceptable space sound pressure level. We talked about this last week. This should be in the project specification or the project brief. If it's not there, well, there might be an acoustic report for the project. That should specify what's required for the space. If it's not there, we can refer to AS 2107, which has got recommended sound levels. And remember that the SPL or sound pressure level may be expressed as an NR level, which is, which is noise rating level. Then the next thing is to go into the fan selection data and determine the fan sound power level spectrum, which is called the SWL from manufacturer's data, and that's usually expressed from 63 through to 8,000 hertz. Then we need to calculate the attenuation required using a system acoustic calculation spreadsheet or some other method. And we looked at the FanTech method last week, which is probably the best one to use at this point in time. So that going through that spreadsheet, it will tell you what attenuation you need to achieve the specified sound pressure level of the space, given the sound source, sound power levels, the ductwork, the fittings, internal insulation, and so on, once you've taken all that into account. Then we go and select an attenuator which provides the required acoustic performance and has dimensions which suit the available space. So if the attenuator is going into a ceiling space, you need to be aware of that there's restrictions on the height and perhaps the width. Then we need to just work through that to get an appropriate size. On a big project, sometimes attenuators can be very large, and we may have to break it down into 2 or more attenuators in series because they're just too big to handle, too heavy. But look, that's probably something you're not going to see soon, but on a large project that can happen. So we've got to think about how the guys on site going to manage to get these attenuators into place. Normally for an axial fan, we would try to use cylindrical attenuators, but this depends on the amount of attenuation required. So as I said, a cylindrical attenuator can bolt, without a pod, can bolt directly onto a fan, but you just need to be sure that that's going to provide enough attenuation. And this is why we quite often use what they call the C tool, which is nominal 2 diameters length. So if you've got say a 600 diameter fan, then the attenuator is about 1200 long, and you'll get a lot more attenuation out of that than you will with the 600 millimeter long attenuator, for obvious reasons. You've extended the length of internal duct, and the attenuator will give better attenuation than a piece of duct. And when we're talking about rectangular attenuators, ensure that the required low frequency attenuation is achieved. Pressure drops less than 40 pascals and face velocity is around 5 to 6 meters a second. If you're using an attenuator which has got quite wide airway width, in other words, you're not looking for huge attenuation, then you can probably increase the face velocity. You can use your judgment there. If your duct velocity is 7 meters a second and you don't need a lot of attenuation, then that's probably going to be okay. But I just mentioned that as something as a bit of a guide to be aware of. In other words, don't have a duct that's running at 10 meters a second and then crashing into an attenuator and trying to squeeze the air through those narrow pathways to attenuate the sound, because it's not going to work very well. You'll end up creating a turbulence at the inlet and regenerating noise. when locating attenuators in the duct system, ensure that the airflow is unrestricted into and out of the attenuator. If you're using a potted cylindrical attenuator, provide a straight duct piece between the fan and attenuator to prevent turbulence, which I mentioned earlier. And don't install attenuators directly adjacent to bends, branches, or other duct fittings which will disturb the airflow. The FanTech catalogue provides comprehensive selection details for a large range of attenuators and also provides a guide for correct installation. I'm going to just show you another extract from the FanTech catalogue. These are installation do's and don'ts, they call them. We've talked about these from the point of view of fans before, but these are for attenuators specifically. So left side, don't do this. Right side, this is a better way to do it. Okay, so the left side in this case, they've got a sharp transition at the inlet to the attenuator. They're saying don't do that because that's creating turbulence. Provide a long transition so that the air has got room to expand into that volume before it hits the attenuator. What tends to happen if you have a short transition like this and the air is traveling along quickly, it just doesn't have time to expand into cover the full face of the attenuator before it goes in. So that's pretty straightforward. And we have had an example of that, Jordan, with your job that we talked about. Has that sort of gone any further as far as you know? Or?
I didn't realise I was muted. No, we're still waiting on the acoustic engineer.
Yeah, okay. Well, then these are things that you're aware of now, so it'll be interesting to see what they come back with, and you'll understand if he does make some changes or tries to improve things, why they're doing that.
Yeah.
Now, the second example here is there's volume control dampers in the ductwork. The first example on the left, they've put them right next to the attenuator inlet, which is obviously, you don't want to do that. Excuse me. So put them further back upstream, again, to let the air straighten out before it enters the attenuator. This one is attenuators in relation to bends. The air's coming along, going around a bend, straight into the attenuator. You don't want to do that because the bend is causing turbulence. Now, there's another thing to notice here, that in this, on the left side, they've got the splitters in the vertical configuration. But over here, they've flipped the attenuator over on the right-hand side, excuse me. They've flipped it over so the splitters are horizontal, so that, and they've extended the length of the bend or put a straight piece after the bend so that the air can straighten out a bit before it goes into the attenuator. And because the splitters are horizontal, that's getting a more even distribution through the attenuator. So that's an important one to be aware of because this can happen a lot. You don't want to put vertical splitters after a bend because you're starving the attenuator of airflow on the inner radius side. Does that make sense? Now I'll just jump onto something else for a second, because this is another important point that you need to become aware of with attenuators. When they talk about dimensions, the length, that's self-explanatory. The width is self-explanatory. But the height, the height is always the length of the splitter. The greater so if you turn that attenuator over, in that picture there, the height is self-explanatory because that's the height of the attenuator. But if you turn that 90 degrees, the height you might think becomes the width. But they call it the H dimension, always stays the same. So whether it's vertical or horizontal, the H dimension is the height. Does that make sense? So I just mentioned that because it can be confusing if you don't know their terminology. Well, it can be confusing. So just remember that the H dimension or the height is the length of the splitter. Okay, whether it's in the width or the height configuration, it's still the H dimension. So going back to, oh, sorry, coming back to this, attenuator position relative to axial fans. So on the left side here, we've got an attenuator again with vertical splitters going straight or with a short transition into a fan. But then on the outlet, again, the short transition into, trying to see the picture here, straight into an attenuator. You get a lot of turbulence on the outlet side here with that short transition, and hitting the attenuator, again, it's just causing issues. So they're suggesting over here, as I've said before, bring the attenuator back a bit, have a longer transition on the inlet, a long transition on the outlet, and that'll help the whole system to work better. It's not only the performance of the attenuator that's affected by this, it's the performance of the fan. So whenever you're causing turbulence around a fan, particularly an axial fan, its performance will be affected. And you'll be wondering why the fan doesn't work properly. Well, that could be the reason, that it's not installed correctly. Attenuator position relative to axial fan again. Now they've got a potted attenuator this time. This is what I said in the notes. You don't put a potted attenuator at the inlet to a fan because the turbulence caused by that and the reduced area that the fan blades can see. That what the fan blades want to see for an axial fan is nice straight flow to the whole face of the fan. If you put a pod there, you're only allowing the air to go around to the outside tips of the fan, and it just won't function properly. So you pull this, if you've got a podded attenuator, pull it back and put some straight duct in between the pod and the fan. What you can do if you have a podded attenuator is ask the attenuator suppliers to provide that extra piece of duct to attach to the fan, because if it's Fantech, for instance, they will supply the attenuators and the fans. So you can just ask them to make the attenuator longer. So finish the pod, say, 1 metre before the fan and increase the casing up to the fan. They can make all that for you, which makes it easier. Silencer position relative to centrifugal fans. So centrifugal fan, the air's going around and spinning out the top. This is showing horizontal splitters. Obviously, the air is being forced to the top of the duct. So the most part of the attenuator doesn't even get to see the air. So you're going to have a very high pressure drop. You're going to try and force the air through one passageway. You get regenerated noise. It's just not going to work. What they are suggesting you do is put a spacer piece of duct in before the attenuator and turn the splitters vertical so that the air's got a chance to pass through the whole attenuator, not just a part of it. There's some recommendations here on acoustic sealing of silencers where they're passing through walls. So if you have an acoustic wall, for instance, and you've got an attenuator that goes through the wall, these are some suggestions on how to do that. Louvers on a silencer discharge. Sometimes they're calling it a silencer here. It's an attenuator and a silencer is the same thing. So it's calling it a silencer this time. This one has got horizontal splitters. It's very close to a discharge louver, and that's just not working. It's causing too much turbulence at the outlet. The best way to do it is to have vertical splitters and create a spacer duct again. Let the air straighten out before it hits the louver. It's all common sense sort of stuff, but it's worth taking note of if you're designing things to make sure it's going to work properly, because I've seen lots of jobs where, say, a consultant designs something and he's putting attenuators right on a bend or right on a branch and they just don't work. You can't do it that way. Same sort of thing on the inlet side. Now this is another thing to take note of: fan position relative to noise sensitive areas. So if you can, don't put a fan or a fan coil unit directly above where people are working, or trying to have a quiet space to function in. Try and put the noise source back over a storage area or somewhere else. I mean, this is common sense again. It's not always possible, but if you can, get the noise source away. Quite often you'll see they're showing a centrifugal fan in a plant room here. That might be an air handling unit, for instance, or it might be a fan. If you need an attenuator, it's better to put it through that wall. If you can do that. If that's a fire rated wall, that makes it very difficult. But if it's not a fire rated wall, if you can put the attenuator through the wall, then you're not only attenuating the noise from the source, from the fan, but you're stopping the breakout noise from the fan breaking out through the plant room wall, which is what's shown on this. They call it flanking transmission. The radiated noise from the fan casing is actually can break into the duct and then break out of the duct, or it can break straight through the wall. With the attenuator there, that just gives you a better sound seal for the plant room wall. This is just talking about passageways through attenuators. Obviously and velocities. So the lower the velocity through the attenuator passageways, the less breakouts you're going to get. We talked about that. Changing direction of airflow. Recommendations on: don't use square bends without vanes. Try and use vanes, or use radius bends wherever you can. It would be my advice. That's what we always tried to do. Is sometimes you're restricted for space and you have to use a square bend, but put some splitters in the square bend to get the air to flow smoothly around the bend. If you've got a branch, do the best you can to get a smooth takeoff for the branch. We don't do these Y-shaped branches very often. We normally have a shoe to reduce the velocity as it enters the bend. And that helps to reduce noise. And so on and so on. So you can have a look at those. They're in the catalogue. And if you do have a situation like like Jordan's situation, this will help you to try and find a better way to do it. But when you're restricted for space, you've got to find a solution. And I think your situation, Jordan, that we talked about it's going to be a bit of a problem, but there'll be a solution. Somebody will be able to work out a better way to do it. You might have to select a quieter fan or something like that. So there's just a few references there. NCC, section J refers to the pressure drop that I talked about. Here a technical manual and here a DA03 have information about duct design, acoustics and so on, and AS2 107. So any questions?
No, that was very comprehensive.
Would you like to do an exercise on selecting an attenuator? Not now, but to follow on from this, we can do a selection if you'd like to. We can do that next week if you like.
Yeah,
I think it's a good idea.
That'll be good.
I don't want to just send it to you and say, ask you to do it, because it'll probably be a little bit hard to work through at the moment. It's probably better if I just talk you through it, and then you can keep those notes. I'll send you the notes. You can keep those notes for future reference if you want something to refer to. But as I said, the Phantech catalog's got it all there. You can go in there and you can work out how to select an attenuator, but we can spend half an hour talking about it next week, and then you might have a crack at doing it yourself. All right, so we'll do that next week. Unless there's something else that you want to talk about. I'm totally flexible. I'm here to help you guys. So, if there's something else you want to talk about, by all means, let me know.
Yeah, no, that sounds great, Peter.
All right. Well, I'll let you get back into it.
Thanks, Peter.
Thank you.
Thank you.
All right.
See you.
See you guys.